For centuries, we've used microscopes to explore worlds hidden from our naked eyes. The familiar light microscope, a staple of school science labs, opened up a universe of teeming bacteria and intricate plant cells. It was a revolution, but it had a fundamental limit. There's a point where no matter how perfectly you grind the glass lenses, you simply can't see any smaller. The very nature of light itself creates a barrier. This limitation, known as the diffraction limit, means that objects smaller than about half the wavelength of visible light become a blur. Atoms, which are thousands of times smaller still, remained firmly in the realm of the theoretical, a concept we could infer but never directly observe. To see an atom, we needed a new kind of light. We needed something with a much shorter wavelength. The breakthrough came from a profound discovery in quantum mechanics, the idea that particles, like electrons, can also behave like waves. The French physicist Louis de Broglie proposed this in the 1920s, and it changed everything. The wavelength of an electron is extraordinarily small, far shorter than that of visible light. This simple yet revolutionary idea paved the way for an entirely new kind of microscope, one that could finally break through the light barrier and give us a direct glimpse of the fundamental building blocks of our world. So the challenge was clear. If we wanted to see atoms, we had to abandon light altogether. We needed to build an instrument that used a beam of these tiny wave-like particles instead. This is the core principle of the electron microscope. It doesn't use photons of light to illuminate a specimen, it uses a focused beam of electrons. By harnessing the quantum nature of these subatomic particles, we could create a probe fine enough to resolve details on an atomic scale. It was an audacious engineering challenge, requiring us to control and manipulate these infinitesimally small particles with incredible precision. But the potential prize was monumental: to finally look upon a single atom. This shift from light to electrons represents one of the great leaps in modern science. It's akin to moving from trying to read Braille with a football to using your fingertip. The scale is just that different. The light microscope showed us the city, but the electron microscope could show us the individual bricks from which it was built. It promised to transform fields from materials science to medicine by allowing us to see, for the very first time, how matter is arranged at its most fundamental level. This wasn't just about getting a better picture. It was about opening a door to a new reality, one that had been invisible to us throughout all of human history. To build an electron microscope, you need three critical components. First, you need a source of electrons, an electron gun. This is typically a superheated filament, often made of a material like tungsten, which boils off electrons when a high voltage is applied. These liberated electrons are then accelerated down a column, forming a coherent high-energy beam. Think of it as the light bulb of the electron microscope, but instead of gentle photons, it's firing a powerful stream of subatomic particles. This beam is the very heart of the instrument, the probe that will ultimately interact with the sample and carry back information about its atomic structure. Next, you need a way to focus this beam. With light, we use curved glass lenses to bend the photons to a focal point, but electrons, being charged particles, don't respond to glass. Instead, they can be manipulated by magnetic fields. This is where electromagnetic lenses come in. These are powerful coils of wire that generate precise and incredibly strong magnetic fields. As the electron beam passes through these fields, its path is bent, just as light is bent by a lens. By carefully shaping and controlling these magnetic fields, we can focus the electron beam down to a spot smaller than a single atom, allowing for astonishing precision and magnification. The final, and perhaps most crucial component, is the vacuum system. The entire journey of the electron, from the gun to the sample and then to the detector, must happen in an extreme vacuum, a space almost entirely devoid of air. This is absolutely essential. If the electrons were to collide with gas molecules, like oxygen or nitrogen, they would be scattered in all directions, disrupting the beam and destroying the image. It would be like trying to take a photograph in a thick fog. Therefore, the microscope's column is pumped down to ultra-high vacuum, creating a clear, unimpeded path for the electrons to travel, ensuring the signal we receive is purely from the sample itself. So you have it, a source to generate the electrons, magnetic lenses to focus them, and a vacuum to let them travel freely. These three systems work in perfect harmony. The electron gun fires its beam, the electromagnetic lenses shape and aim it with pinpoint accuracy, and the vacuum ensures it arrives at the target undisturbed. It is a marvel of engineering, a delicate dance of high voltage, powerful magnetism, and profound emptiness. Together, these components create an instrument capable of navigating the nanoscopic world and revealing the secrets held within the atomic arrangement of matter, something utterly impossible with conventional optics. The reason an electron microscope can see atoms while a light microscope cannot comes down to one word: resolution. Resolution is the ability to distinguish between two closely spaced points. As we discussed, light's wavelength imposes a strict limit. The wavelength of visible light is between 400 and 700 nanometers. The rule of thumb is that you can't resolve anything smaller than about half the wavelength of the probe you're using. This means even the most perfect light microscope is stuck at a resolution of around 200 nanometers. An atom, however, is typically around 0.1 to 0.2 nanometers in diameter, 1,000 times smaller. It's physically impossible for light waves to resolve them. They are simply too big and clumsy. Electrons, on the other hand, have a much shorter wavelength. Thanks to de Broglie's wave-particle duality, the wavelength of an electron depends on its speed, and by accelerating them with high voltages, we can make their wavelength incredibly small, picometers even. This is the key. A shorter wavelength means a higher potential resolution. It allows us to see much finer details. This is why electron microscopes can achieve resolutions well below a nanometer, easily breaking the atomic barrier. They provide the fine-tipped probe necessary to map out a landscape where the features are individual atoms, a feat that light waves, with their comparatively enormous size, could never achieve. This incredible power was first demonstrated in a historic moment in 1970. A physicist named Albert Crew and his team at the University of Chicago used a custom-built scanning transmission electron microscope to achieve the impossible. They managed to capture the first-ever direct image of individual heavy atoms, in this case uranium and thorium atoms, placed on a thin carbon film. The resulting images were just a few fuzzy, bright spots on a dark background, but their significance was earth-shattering. For the first time in history, humanity was not just inferring the existence of atoms. We were looking right at them. It was a profound confirmation of atomic theory and the dawn of a new era in science. But how do we get from a beam of electrons to an image? The concept is called contrast. When the electron beam hits the sample, the electrons interact with the atoms within it. Some electrons might pass straight through, while others are scattered or deflected by the dense positively charged nucleus of an atom. A detector placed below the sample measures how many electrons get through at each point. Where there is a heavy atom, more electrons will be scattered away, and that spot will appear darker in the final image. Where there are fewer or lighter atoms, more electrons pass through, creating a brighter spot. It is this variation in scattering, this contrast, that allows us to build a map of the atomic positions. There are two main types of electron microscopes, and each offers a different perspective on the atomic world. The first is the Transmission Electron Microscope, or TEM. In a TEM, a broad parallel beam of high-energy electrons is fired through an extremely thin slice of the sample, typically less than 100 nanometers thick. As the electrons pass through, they are scattered by the atoms in the specimen, as we've discussed. The electromagnetic lenses then collect these transmitted electrons and project them onto a detector, forming a two-dimensional black and white image. A TEM is like a slide projector. It gives you a high-resolution view through the object, revealing its internal structure, crystal lattice, and even individual atomic columns. The second type is the Scanning Electron Microscope, or CM. Unlike a TEM, and SEM doesn't look through the sample. Instead, it uses its electromagnetic lenses to focus the electron beam into a very fine probe, which is then scanned back and forth across the sample's surface in a raster pattern, like an old television screen. As the beam hits the surface, it knocks off secondary electrons from the sample's atoms. Detectors collect these secondary electrons, and the number collected from each point is used to build up a picture, pixel by pixel. This technique provides stunning three-dimensional looking images of the surface topography of a specimen, but with much lower resolution than a TEM. So, the choice between TEM and SEM depends entirely on what you want to see. If you are a material scientist wanting to see if atoms in a new alloy are perfectly aligned, you would use a TEM. You would slice your material incredibly thin and look through it to see the crystal lattice directly. If, however, you are a biologist wanting to study the intricate surface of a pollen grain or an insect's eye, you would use an SEM. You would coat your sample in a thin layer of metal and scan the surface to get a detailed three-dimensional like image of its features. One looks inside, the other looks at the outside. Ultimately, the ability to visualize atoms has revolutionized science and technology, from designing new medicines by seeing how a drug molecule binds to a virus, to engineering next-generation computer chips by checking the placement of atomic layers. Electron microscopy is at the forefront. It has turned the abstract concept of the atom into a tangible reality we can see, measure, and manipulate. Each image of an atomic lattice or a viral protein is a testament to human ingenuity. It's a reminder that with curiosity and cleverness, there are no worlds that are truly invisible, only worlds we haven't yet found the right way to see. And that is a truly wonderful thought.